Hi, I'm Alex Sottenmurray. I'm a mechanical engineer at Hexagon, and I help students and professors put our simulation software to work. In this video, I'll be talking about how the block tool in MSC Apex works. This builds on a previous video on simply modeling stress and strain in Apex using that tool, but this is more talking about how it works. The previous one is a how-to guide. I'll have a link to that in the description. Also in the description is the video on transverse shear and bending, which shows you how to build a model from scratch. And if you can do that, you can do what you would need to do from this if you wanted to do this one totally from scratch. The next thing that I want to talk about in this video is what are the notional scenarios that we're trying to represent that you might see in a textbook. How do we turn that into a simulation? It's more complicated than you would think. So let's go look at some diagrams. I have illustrations of two scenarios here for normal stress and shear stress. With normal stress, the block is anchored to the ground and there's a force pulling it up, or you could have the force pushing down. It doesn't really make a big difference. For shear stress, we have the block anchored to the ground and we have a force moving to the right, okay, so parallel to the ground. This leads to a different type of stress state. It would be really great if we could model these and see what uniform stress looks like and how it affects just, a simple cube in a finite element analysis model. I'll show you what it actually takes to get this working in MSC Apex. I'm going to go to Apex now. I'm going to show you how the loads are applied and then how the constraints are applied, and then we'll just go step by step through the other aspects of the model. First, let's generate a block. I will click Education, Block, and the green Apply checkmark. Next, I click on the Model tab, and I click this button to expand all containers, so we can see all the components of this model. Let's look at the force first. We have a force of 10,000 newtons in the y direction and 0 in the x direction. Note that this force is applied as something called a pressure, which might be better labeled as a stress. What Apex calls a force is really a point load. If you want a force applied smoothly across a surface, pressure is really what you want to use. Now let's look at how this part is constrained for normal stress. And I'll rotate the part so we can see its bottom a little bit better. It is constrained in the y direction across the entire bottom surface of the cube. So all of this is working together to keep the part from lifting off of the surface. The part is constrained from motion in the x direction along the z-axis and against motion in the z along the x-axis. These x and z constraints are not applied across the entire bottom of the cube because when the cube is pulled up, it will stretch out, but it will also narrow. And if we had the bottom really fully constrained in the x and z directions, it would fight that narrowing, and we would wind up with very large stresses near the bottom. So this doesn't correspond exactly to a real-life scenario, but is exactly what we need to be able to see uniform stress. Next, let's take a look at shear and see how things would be a little bit different for that. So I'll click again on Block, click on Shear, and click the green Apply checkmark. Let's look at the force. What we see is exactly what we saw before, except now the force is 10,000 newtons in the x direction and 0 in the y. Let's look at constraints now. We don't expect the bottom surface of the block to change in size based on an applied shear load, right? Because it's not under tension and so it's not undergoing narrowing due to the Poisson effect. Therefore, we can constrain against x motion all along the bottom surface and that doesn't make a problem. The z direction constraint is unchanged. It is also not very important because we don't have any force in the z direction. The y direction constraint is kind of funny, so let me try to explain this one to you. We constrain not just the bottom like we do for normal, but we also constrain the left and right hand sides. If we did not constrain those, the block would actually be under a combination of this pure shear load and a bending load. So that winds up giving you a non-uniform stress profile. The picture that I showed earlier with a single arrow pointing along the top of the block was a little bit of a trick because in truth, pure shear loading requires arrows going in multiple directions to be able to give a balanced state of stress. Still, this corresponds to something physical that's meaningful, like the sole of a shoe is using shear stress to propel somebody forward, but it's not really under very much bending because the sole is very thin compared to how wide it is. These left and right hand boundary conditions approximate that effect. Now I will double click on the Y constraint and modify it so it only points to the bottom surface. You'll see how important those side constraints are. So I will select just the bottom face of the cube and hit the green apply checkmark. Before I hit run, let me tell you about the other aspects of the model. The geometry is created with something called the box tool. You can learn about that and many other things here from the transverse shear and bending video. The mesh is much finer than you would need for a part that is under such uniform loading, but I use a very fine mesh here so that we see the stresses in the part in a very smooth way. We are using quadratic elements, which can give very good accuracy and be very efficient. The other details here are for advanced meshing. The part is steel, and that's applied with a steel element property. I'm going to run the simulation now, and then we'll take a look at something called the Studies tab. So before we go to Post, let's look at the Studies tab. This is how we tell Apex the type of simulation that we want and which loads we want applied to the model. Sometimes you need to come into Loads and Constraints to manually apply a force or a constraint to your model. The interface for this is different in the new scenarios in Apex, but for educational purposes, for now, the legacy scenarios that have this interface work perfectly fine. Another thing in here that is good to know about is simulation status. If you see all good check marks, that means that the model ran fine. This is great to refer to if you do have trouble getting your model to run. The block tool does a lot to set up scenarios for you, but if you were building a model from scratch and really wanting to control which parts are in the model, this interface is very helpful for that. Now let's go to Post. We'll click Block and Make Post. Remember that we're looking at shear, but without constraints in the Y direction on the sides of the block. The top of the block is now tilted, causing us to have compression here and tension here at this corner of the block. These stresses are distracting from somebody's first experience learning about shear stress, and that's why this particular tool has those constraints. It lets us focus on what you see in a pure shear stress state. I hope that clarifies how the block tool works, and if you've gone from never having done FEA to done some modeling just using the block tool, that this would help you take the next step in learning how to do finite element analysis modeling. If you have any questions, leave them in the comments or send me a message on LinkedIn. Information on how to get in touch with me is in the description. And if you're a professor and you're interested in teaching solid mechanics with Apex, get in touch. Again, contact info for that is in the description. We have associated curriculum resources that would make it easy for you to embed this in your class. All right, have a great day. Bye.